All right, good morning, everybody. Welcome. How's everybody doing today? Yay, awesome. I'm David Smith. I am one of the cloud advocates from Microsoft, and this is the second talk in the Artificial Intelligence and Machine Learning path. Now, who was in this room just a few minutes ago for Seth's first talk in the series? Awesome. Great talk, wasn't it? I've got some bad news. I'm not nearly as funny as Seth. I'm sorry. But we are going to cover some really cool stuff today. We're going to actually be wading into those waters of artificial intelligence at about knee height for this session. We're going to be using pre-built artificial intelligence services that you can plug into your applications without any need to understand the mathematics behind artificial intelligence. But I am going to tell you a little bit about those mathematics because it is useful to understand how they can go wrong and, more importantly, how you can make them go right. Now, there are going to be lots and lots of links and information and resources and demos in this talk today, but don't worry, everything you need to recreate everything that I do is available online, particularly at the GitHub repository that you can see at the second link right there. The demos I will be giving are going to be pre-recorded, and I'll run you through them as you go. You'll understand why they're pre-recorded if you've tried to use the Wi-Fi here this week. But like I said, you'll be able to actually find all the data and all of the scripts and even a single click to deploy to Azure button for the entire application I'll be using so you can verify that everything I'm doing you can do yourselves as well. I'll show this slide again at the end of the presentation, so if you've missed it now, don't worry, it's going to come back. So in this talk, I'm going to be using those pre-built artificial intelligence services to add human-like capabilities to applications. But what does human-like mean? And there are lots of things that you could do to add applications to your apps that are like the things that humans can do. For example, being able to add the power of speech to applications, being able to make your application see, so you could do things like being able to search for photos or search photos by content. You could give your applications human-like intuition in a way that they could automatically rearrange elements of user interfaces to meet expected human needs. You could give your app the power of speech to be able to translate text or speech, and even in other people's languages, and internationalize your applications like that. Or you could automate the human process of looking at data rather than having a human look at a sequence of numbers and trying to identify spikes or outliers. You could have a machine do that process and then scale it up to really, really huge volumes as well. So they're just some examples of the human-like things that you could do with applications. But does it take a lot of expertise to implement these kinds of things? And what I hope to show you in this presentation today is that that answer is no, because we have in Azure Cognitive Services that provide simple API calls that you can plug into any application to put these human-like capabilities into your applications. Azure Cognitive Services has more than 24 APIs, but at the broadest level, they offer capabilities within these categories of human-like capability. Vision, so that's all about understanding the content of photographs and drawings, text and handwritings, even video. Looking at speech, so we provide tools that enable you to recognize speech and generate natural human-like spoken voice, even in your own voice, if you wanted to do that. On the language side, being able to understand the content and the content of written documents and text, and also translate between human languages. We saw a lot of that in Seth's talk in the previous session. Decision, now that's a brand new category for Azure Cognitive Services, which is all about making human-like choices about data, content, and application user interfaces. We're going to be going into that one in a bit of detail today. And finally, there's search, which, as you saw in Seth's talk just a moment ago, which is all about being able to understand and answer natural language questions about the content of large, unstructured data stores. So as I said, the search category we covered in the previous talk, but in this particular talk, we're going to cover just 3 of those cognitive services. That's computer vision, which is all about how we're going to use these AI services to recognize the content of a photograph for a product-based application. And then we're going to enhance that with something called computer vision. So we can enhance that custom vision to recognize specific objects that our retailer sells. And we'll be using the brand new personalizer service that just went into availability this week which will automatically adapt the layout of a user interface by observing customer preferences and activity and present the best product that any user might be most likely to click at, even if they're an anonymous user. But remember, for across all of the Azure Cognitive Services, the principles of setting things up and using cognitive services are the same for all the APIs. So what you learn in this session today, you'll be able to apply to any of the Cognitive Services APIs you see listed there. So first, we're going to take a look at pre-built AI for computer vision and how we can use cognitive services to give an application the ability to see and then customize it for our particular needs. And we're going to do that in the context of Tailwind Traders. Now, you might have seen Tailwind Traders in other presentations this week. It's a fictitious retailer we developed to give some story behind these applications. The Tailwind Traders website is like any e-commerce retail website. It's got the ability to search for products, make purchases, and it's got one particular AI feature that we're going to enhance in here as well. Once again, even though this is all fictitious, I'm going to give you all the source code behind everything I show here at the link at the end of this slide so you can duplicate this yourself. So let's go live to the Tailwind Traders website. And one of the AI-enabled features that we have in here is this shop by photo feature that you can see in the center. And this feature allows the customer to upload a photo of a product they might want to purchase, and the idea is the app will then tell them if it's available and where to find it. So we'll go ahead and upload this photo of a drill, and you can see it's being uploaded to the search now. The application recognizes that was a photo of a drill, and tells us we have this drill in stock, and also where to find it in the store. Now let's go ahead and try that same service again with a different picture. Click on the Upload a Photo button right there. And this time let's choose that picture of a pair of pliers there on the right-hand side. We'll upload that to the website, and it hasn't quite worked because it has recognized that particular picture of pliers as a hammer, which is not what we want it to do. So what we're going to do now is dive in a little bit to figure out what went wrong there, and then show you how you can fix it. So to do that, it's going to be helpful to dive into a little bit of that theory I mentioned to understand how computer vision works. Don't worry, there's not going to be very much math in this, in fact, very little at all. But understanding a little bit about how computer vision works is going to help us understand what went wrong just there. Now, not long ago, being able to give a computer a photograph and then it being able to give us useful information about what was in that picture, I mean, that was literally the stuff of science fiction. You would see it on Star Trek. But this XKCD comic was published almost exactly 5 years ago in September 2014. And now, just 5 years later, a computer can easily tell whether a photo was of a bird or any other kind of an animal, thanks to the advent of big data, GPU computing, and convolutional neural networks. And that's what I want to show you now. This explanation I'm about to give is adapted with permission from Brandon Rohrer. Brandon's got a really excellent blog that has a bunch of video tutorials with in-depth explanations of many aspects of AI and machine learning. Do check out Brandon's blog for all the details, because I'm only going to be able to give a quick sketch in the time I've got right here. So you've all probably heard that AI is powered by something called deep learning. Now that deep in deep learning, that does not mean profound or anything like that. All it means is that we take an image and we pass it through a neural network. That's what you see on the screen right there with many layers. So the deep just means deep numbers of layers in a neural network, and that's it. The one we have here, though, is a very, very simple neural network. It has only 5 layers, as you can see right there. And real-world vision systems will have many dozens, maybe hundreds of layers. And this one that you see on the screen is designed to take an image as input and then classify that image as one of exactly 4 objects, either dog, bicycle, apple, or tennis ball. And that's it. It can't tell any other types of objects except the one that it has been designed to detect. So when a neural network has been trained, and we'll talk about what that means in a second, it passes the input image through the network layer by layer, at each layer transforming the image into different smaller images. Now each layer recombines the images generated by the prior layer and then the images get smaller and smaller until at the very end, they just become a single pixel with a value between 0 and 1. And that number between 0 and 1 represents the confidence that the neural network has detected that particular object that's labeled there on that right-hand side. And the more confident it is, the higher that number is and closer to 1. So in this case, you can see we've inputted a picture of a bicycle on the left-hand side of the picture. It passes through all those nodes to the far end until the number for the node bicycle on the right-hand side is 0.93. That's the highest number. So this particular neural network has correctly identified that that is a bicycle that was input there on the left. But how do you train a neural network? How do you figure out what to do at each of those stages to get those numbers there at the end? The trick is that each of those round circles, those nodes in the neural network, that's basically just a filter. Same kind of idea as a Snapchat filter or an Instagram filter, but instead of making the image sepia toned or putting bunny ears on all the faces, it's doing something very different. And if I think something that we don't even know ahead of time, it actually learns what kind of transformation to make in such a way that the labels there on the right-hand side give the right answers through that training process. So let's see what that is. It's all done through these filterings. So let's start with a simple image. So this might have been the image of a bicycle, but just to make things simple, let's do this very simple image of a cross. It's 9 pixels by 9 pixels, and the white pixels are the +1s and the black pixels are -1s. So we're going to apply a filter to that image just like what happens in each of the nodes of a neural network. So to transform that image, we're going to apply a 3x3 grid of weights, and that represents our filter. And actually small grids like this, 3x3 or 5x5, that's pretty typical for computer vision systems. The only difference is that in real computer vision systems, the weights aren't round numbers like this -1 and +1 that I have in this grid. They'll typically be numbers in that range, but they'll look pretty random. So to apply that grid of weights to this particular image of a cross, we overlay the grid of the weights centered on a particular pixel in the image, and then we multiply each of the weights by each of the pixel values and take the average. And that average then becomes the pixel in the transformed image of the next layer down in the neural network. Pretty simple, right? One thing you've probably noticed is that we can't use the very edges of the source image because the weights grid wouldn't overlay without missing the edges of the picture. And that's one of the reasons why the picture gets smaller and smaller as we go through the network. And there are other reasons as well, but that's basically why we get smaller images as we go down. Here's just another example. So I've moved that grid of weights 2 pixels to the right and 2 pixels down, overlaid it over the images again. Now when we multiply the weights by the pixel values, we get a different average, this time 0.55. So that would mean in our output image, we'd get a gray pixel. And then we repeat that process over all that entire image and for all the copies of the image that flow through the neural network. Now, by the way, this process of sweeping the weights across the image, row by row and column by column, there's a fancy mathematical term for that called convolution, but it's a really simple process, as we've just seen. But this is why they're called convolutional neural networks. So now that we know that each of those nodes, each of those circles in the neural network is a transformation of its input images, and that in turn is determined by a grid of weights. And so the trick, therefore, to training a neural network to recognize objects is to pick those weights in such a way that the right numbers come out at the end. And the way we do that is with training data. We provide this neural network with lots and lots of images. In our case, lots of images of dogs, lots of images of bicycles, lots of images of apples, and lots of images of tennis balls. And we know ahead of time what each of those images represent because a human has looked at them and labeled them like that. And then all we need to do is pass all of those images that we know what they are through the neural network and then choose all those weights in such a way that the right numbers, or the right labels come out with the highest number at the end each time. Often that's not possible, but at least we can choose weights so that the images at the end are labeled correctly most of the time. And that's the training process. Now in the real world, there might be millions of weights to choose, and there might be millions of labeled images to process through that neural network. So how do we compute all of those weights? And this is the points where most talks on machine learning and most books on machine learning will start diving straight into the mathematics. This is where we'd start talking about things like backpropagation and learning rate and cost function. But unless you're an AI researcher, you can ignore all of that for a couple of reasons. First, if you did want to actually dive down into this math, there are lots and lots of great tools that will help you do those computations. And they'll do that by taking advantage of big computing resources and things like GPU compute processors. You might have heard of tools like TensorFlow or PyTorch that can do those kinds of things. I'm not going to talk about those, but the AIML20 talk later in the day by Ari Bornstein will, so check that out if that's what you're interested in. Also, even if you want to make use of all those tools, you would need some good computing resources available to you, as I just mentioned. You'd also need a team of AI researchers who could sort of make use of them all. But instead of setting up that team and having all those resources, you could just make the use of somebody else's research department that has spent a lot of time and a lot of expertise and a lot of data to train up a neural network just like we saw, and then you could just use that yourself. And that's exactly what we've done with Cognitive Services Computer Vision and made that available to you through an API. So with that, you get access to a pre-trained convolutional neural network, so all the weights have already been determined for you. So all you need to do is pass in your image to the neural network, or in our case, through the API. It will do all those computations for you and then give you the value that represents that particular image. And we can even get more complicated than that. Even go beyond just classifying an image as one object type. We could actually do things like detect multiple objects in a single image and even tell you where they are. And that's available for you as well. So now let's actually try out one of these pre-trained AI models with Cognitive Services Computer Vision. So this is a service that will take an image that you provide, either as an image file or a URL directly to an image on the web, and then it will give back to you tags or classifications for the objects that it detects. And those are the labels that we saw in the neural network you saw a minute ago, associated with the most probable objects that it detects. But instead of doing this yourself, you're using a powerful neural network that we've developed at Microsoft that can classify thousands upon thousands of objects. There's a really simple web-based user interface you can use to try it out, and I'm going to show it to you just in a moment at aka.ms/try-computer-vision. We're going to start with that because that's just an easy way to see how it works. But then we're going to dive in to have a look at it doing it programmatically. All right, so this is the Cognitive Services Computer Vision webpage. So if you go to that page and just scroll down a little bit, you can see there's this nice web-based form where you can upload an image for analysis, either from the web or as a file. So I'm going to just click on the Browse button there to choose a file from my desktop and choose that picture of a man in a hard hat. And once it's analyzed that image, which just takes a few milliseconds, it will come back and show us the object detected in the image on the left-hand side. So there's two objects there, the purple one and the blue one. But on the right is the stuff that we actually want to get access to, which is the JSON output with a detailed analysis. That gives us things like all the names and the locations of the objects detected in the image, a list of tags or labels of things associated with that image, and also things like a plain language description of the image, which is useful for, say, photo apps. This one comes back with a man wearing a helmet, and there's lots of other useful information that comes out of that as well. So we can see here in this screenshot of the objects section of the output that two objects have been detected in this particular image. We've got headwear and person, so you can see that right up there at the top. We're more interested in the tag section, which provides a classification for the overall image, which is what we need for our app coming up in a minute, along with the associated confidence scores, those numbers from the right hand of the neural network. The first thing it detects is man, but we're looking for product, so let's look a bit further down. But the second image it classifies as is headdress. And that's not really what we're looking for because we're building an app for a hardware store which does not sell headdresses. As it turns out, this particular API is not trained to detect hard hats. It does detect helmet, but not hard hat. But remember, a neural network can only detect those objects that it has been trained for in the first place. So it doesn't work for us in this particular case. Now, we've done this just by using a web form and uploading a picture and looking at the results on the screen. But if you want to embed this capability into an app, you want to do it programmatically. So let's look at how we can do that now. So you can interface into the Cognitive Services APIs using any language that can connect to an HTTP endpoint. But what I have here is a bash script that I use to connect to the Azure CLI to create some resources and the keys and things that I need to access it, and then connect to the computer vision API using curl. Now, of course, you can install the Azure CLI in your local shell, but here I'm using the Azure account extension in Visual Studio Code to launch a cloud shell, which means I don't have to install anything on the local environment. But once that shell's ready, I can execute commands like this directly from the script. So with this command, I'm just creating a resource group, which I'm going to use to hold the keys, which I need to access Cognitive Services. And now with AZ Cognitive Services, I'm generating those keys. So I'm just going to run that code directly in the Cloud Shell. And now I just need to display those keys so I can get access to them. And as Seth said, I've invalidated all these keys, so no need to copy those down. And let's just copy that first key. You can use either of those two keys. And I'm going to take that key and put it into an environment variable for use in the next part of the script. I also need the endpoint where I can access the cognitive service online, and that's actually provided to us by the service itself. And that depends on which region you're running it in. But now I can grab the URL of an image, and that's the same image of the man in the hard hat we saw just a moment ago. So I'm just grabbing it off the web instead of off of a file this time. And then passing the key to the endpoint with the URL of the image as a JSON string, and then having a look at the results that we get back from curl. And you can see all we have there, and that's exactly the same output that you saw in the web interface a moment ago, where the first two things that were detected were man and headdress. And there you can see it there. So let's actually try that again, just with a different image, because we're doing things programmatically this time. So all I need to do is change my environment variable for the image to a different image. And in this case, we're going to point to a web version of that picture of a pair of pliers. Sorry, no, of the drill. And now let's pass that different image into the same code to run the cognitive services on that new image. And if we just scroll up to the top to have a look at this output here, we'll see what the Cognitive Services API returned for us. There we go. And looking at the tags of the image, you can see that the first one that it's classified for us is camera. And that's also incorrect. We wanted to grab drill back from that so we could search for it in the API. So what went wrong there, and how can we fix it? Long story short, the basic problem is that we're using too powerful a neural network. It can detect too many different kinds of objects, and it can mistake one thing for another. But in our particular case, we just want to build an app that can recognize the specific objects that Tailwind Traders sells. Let's say it was only 5 different objects. So let's train a specific neural network that can just detect those kinds of things and won't get things mixed up. Fortunately, we can fix it using neural networks once again. So what if I told you that there's a way that we can start with a vision model that's been trained for many, many thousands of images, just as we saw, but then adapt it to identify just those objects that you're interested in for your application, even if those objects weren't part of the original training, even if the original neural network wasn't even able to detect those kinds of objects. It might be something completely unique, like your own brand or a brand new product. You can actually train one of these computer vision systems to detect even those. Let's see how it works. Let's go back to the neural networks. We've got the same convolutional neural network from before, but something is different, as you can see. We've stripped off that final layer. So that final layer with the object classifications has gone. And what we're left with is just the images that were generated at that second to last layer. I've labeled them F1, F2, F3, and so forth. Let's even forget the fact that they're images. Rather than being 3 by 3 images by the time we got down to there, let's just think of that as data, 9 data points. So what we can do is feed a new image there on the left-hand side, do all the same calculations with the same weights as before, but at the end of the day, what we get out is not a classification, but we get a sequence of 9 data vectors that somehow represent that image. Now, we don't really know what these features are in any real sense. All we know that those features were useful in classifying those millions of images that the original neural network was trained to classify, and it turns out they're also useful for classifying other kinds of images as well. Things those features might do, just as examples, is one feature might detect greenness in an image, and that feature turned out to be useful in detecting things like tennis balls or lawns, but it also was useful in detecting other kinds of green things. Another one of those features might have detected circular features in an image, and that turned out to be useful for detecting bicycles, but is also useful for detecting hula hoops and other kinds of things as well. So we can use that fact, and it's a trick. We can take those features that are generated by the old neural network, collect the values with new images, and use that to build a new model, as we'll see here. So let's suppose that we wanted to train a brand new model based on the old neural network to identify hammers and hard hats. So we can paste in an image of a hammer on the left, run it through the neural network, collect all the features on the right, so that'll give us 8 data vectors, 1 for each feature, and it also gets us a binary variable, a 1 or a 0, and we'll get that for each image that we put through. Same thing with hard hats. Take a picture of a hard hat, process it through the image, collect the features, get another binary variable, 1 or 0 for hard hat or not. Let's do that for a few dozen, few hundred images. So what do we get? Now, if you're a statistician or a data scientist, you probably know where I'm coming from this. After we process each of our few hundred images, we get a sequence of values, features, a binary indicator. What could we do with that? We could build a logistic regression model. We could build a 1-layer neural network, a very simple predictive model we can take from those generated features in our binary values, build a new predictor just from that, and it turns out that that works really well. You don't even need a lot of data. A few dozen images will often do the trick, as long as the things you're trying to detect are visually distinct and those features can identify them. You also need a lot of computing power. It's a simple logistic regression or a 1-layer neural network, so you don't need a lot of power to do those computations. Now, this is obviously a toy example, and you'll likely want to identify more than 2 objects, and the underlying neural network will generate many more than just 8 features at its second to last layer. But the principle remains, you can do this with modest data and modest computing power, and it often works really well. And of course, you don't have to build that transfer learning model, that's what it's called, by yourself. You can use the advanced vision models we just saw in computer vision as the base, and then provide your own images and classifications and use the service called custom vision. Now, just like computer vision, you can train transfer learning models programmatically using a web-based UI, and that's what I'm about to do here. But you can also do it programmatically using curl as well, directly through the API. So anyway, now I'm going to use Microsoft Cognitive Services custom vision to train a model for that shot by photo feature we saw earlier on in the Tailwind Traders website. So here I am in the custom vision web-based interface, which gives us this nice UI where we can provide new images for the transfer learning analysis. And as you can see in this project, I've already uploaded a number of pictures. We've got here pictures of screwdrivers. Further down, we've got pictures of pliers. I've also got drills and hammers. And I'm going to use those to train my custom model. Let's also add one other classification, which is hard hats. So I'm going to click on the Add Images button up there to provide some new images directly from a folder that I have on my hard drive. There we go. And I'm going to browse to that hard hats folder. Just press Control-A to select them all. Click Open, and now it's uploading those images of the hard hats to the service as well. But I've got to label them as a human. So I'm going to put the hard hat label associated with those images as well, and that'll be used in the training process. And it's going to take just a few moments to upload those files, but while it's doing that, just have a look there on the left-hand side where you can see the counts of the images associated with the 5 categories or labels that I'm working with here. Once those hard hats have loaded, there's only going to be about 180 images, just a couple of dozen per classification. But it's actually, as you'll see in a moment, despite the low number of images, it's going to work pretty well. So now that we've got our images in there, all we need to do is click that train button. So I'm going to go ahead and click train. Quick training works really well. You can actually spend a bit more time with the advanced training, but it's not necessary in this case. But as you can see, in just a few seconds, it has built that transfer learning model and generated something with an overall performance of 99%. Now, when you actually use this in practice, there's something called this probability threshold here on the left, and that's really important. And that determines when we actually, the amount of the probability that we have to get to before we'll assign any classification at all. Now, if it's low, that means you'll give a classification even if the model's not sure, but you'll make a lot of mistakes. If it's high, that means a lot of the time you just won't give any classification at all, but you can be pretty sure it's right when you give one. Now, choosing that is really important and depends on the application. If this was an application, say, for detecting cancers in an X-ray, you probably want to have a pretty low probability, a pretty high probability threshold because you don't want to make false diagnoses. But for this app, a low one is fine. Anyway, I've clicked on the test button to go ahead and train this model so I can upload a new picture it hasn't seen before. So I'm going to browse in here to my test images and choose a brand new image and see how it does on this. I'm going to choose that picture of the man in the hard hat that we've already seen before, and you can see it classifies that as hard hat, not headdress, with probability 99%. So that's looking good for what we want to do here. Let's actually try it on a couple of other images. Choose here that image of a drill, see how this one does. Okay, and it gets 94.5% confidence classification for that drill as a drill, also very good. Lastly, let's try that picture of the pliers we had so much trouble with before. Okay, classifies that as pliers with 99.9% confidence. So this is all looking good. This looks like a model that we can embed into our Tailwind Traders app. Now, the way we embed these models into applications is by exporting them. So now that I'm happy with the model, I'm going to go ahead and click on the export button there. Now you can export in a format good for Android applications or for iOS applications. I'm doing a web application here, so I'm going to export it in a universal format called Onyx, and then download that Onyx representation of our new model for detecting hard hats and so forth directly to my hard drive, as I've done right there. Just a quick aside. So we just exported our model in the Onyx format. Onyx, or Open Neural Network Exchange, it's an open standard that was launched by Microsoft and Facebook to promote the free exchange and deployment of artificial intelligence models. And it's supported by a huge range of applications and tech vendors. So now that we've trained our custom vision model, we're going to integrate it into that Tailwind Traders web app that we saw before. And for that, we're going to use Onyx Runtime, which is an open source inference engine that gives you functions that allow you to generate predictions from new images based on the model that you provide in the Onyx format. So now that we've created our custom model, we're going to call it in the app using its API. The way this is going to work is that we create a new inference session based on the Onyx file, and that's what that file path variable is referring to, that Onyx file we just generated. We're then going to generate a classification label from the uploaded image as a string. There's a bit of work here that I didn't show about sort of reforming that image to the right size, but you can see that in the code. But then all we need to do is take the classification that came from Onyx Runtime and then pass that to the existing search capability in the Tailwind Traders app, and that's what I'm going to give us the results that the user sees. So let's see how that works. Now, that model we just exported from Custom Vision is actually a zip file that contains the Onyx file. So you've got to open up the zip file, and you'll find there's a manifest file there. We don't need that. All we need is that model.onyx file, which is actually the representation of the newly trained neural network. But within the Tailwind Traders website, in the file tree, there's a file called products.onyx, which is driving the existing image recognition system, which isn't working so well. So to fix it, all I need to do is take the model.onyx file we just exported, rename it as products.onyx, and then upload it into the Tailwind Traders application. So let's go ahead and do that now. Now, the Tailwind Traders website, we created in App Services. So I'm just going into the Azure portal, having a look at the App Services app, which drives the Tailwind Traders website. And if you haven't seen it, there's a cool feature within App Services, which is the Advanced Tools, which will give us a Kudu interface to interact with the running website. So just launching that right now. Okay, and from that, you can go to the debug console. I'm actually not going to use Command or PowerShell. All I'm going to do here is just browse through the file system itself to sites, wroot, standalone, and then the Onyx models folder, which is where that existing products.onyx file lives. Then I'm going to grab the one that I just exported and extracted from the zip file from my file system. There it is. And then just drag that over into Kudu, which is going to replace that existing file into the file system. Once that's done, all I need to do is go ahead and restart the website. Just browse through the App Services page there and click the Restart button, and then restart the app. And then within about 60 seconds or so, the app will be ready to use again with its new capabilities. So let's have a look at that now. By the way, before we go back to have a look at the app, I just want to show you a real cool little tool for those of you that want to dive a little bit into the details. There's an application called Netron. It's written by a guy called Lutz Roeder, which allows you to inspect the contents of the neural networks that exist within Onyx files. So if you just go to his web app, I can do that there, click Open Model, and load in that products.onyx file that we just generated, and have a look what it's actually doing. So we can see the details of that neural network. If we scroll in a little bit on the top there, you can see that the input is an image. It's a 3-layer, there's the 224 by 224 image. That's a little bit of a dirty secret about computer vision models. Their inputs are actually pretty small. 224 by 224 is about the size of a Windows icon. So computer vision systems actually have pretty bad vision, but they work really well because they can analyze the contents of those images so well. So now let's zoom out a little bit, and we can scroll through all the layers of the neural network that Custom Vision generated for us. So this is the same representation of those neural networks that we have in look earlier on, and you can see all the layers as we scroll through that there. And as we get to the bottom, we can see how it generates the outputs. One thing it generates is a sequence of 5 numbers, and that's the probabilities associated with the 5 classifications that we train that model on. So that's just the classifications of those values. We also get another vector, which is the loss function, which is those probabilities. And you will need to choose your own probability threshold over which those probabilities need to be before you assign a classification or not. And that, as I said earlier on, that depends on the application. But now I'm back at the Tailwind Traders website. Let's try out our new products.onyx file. So I'm going to browse again to that image that was giving us trouble earlier on. Once again, you have these images yourself in the repository. And let's choose again that pliers thing that gave us trouble before. And now, Tailwind Traders has correctly identified that as pliers, and now our shop by photo feature in the app is working. All right. I've only got time for one more quick example of pre-built AI, and this one comes from the decision category in Cognitive Services. There's something called the Personalizer service that lets us customize the interface of apps in real time, balancing on what the user is most likely to do, coupled with the things that we would like them to be doing. So we can see how this might work in the Tailwind Traders website. You might have seen that recommended section on the screenshots I showed you earlier on, which shows a selection of the departments in the store. There's this large hero image on the left and a few other smaller images for the other departments. And what we're going to do is have the Personalizer service choose for us the order in which those sections appear through an AI technique called reinforcement learning. Now, Personalizer has actually been in development and in use at Microsoft for many, many years. If any of you have an Xbox, the home screen on the Xbox, and whether you see a new game or an invitation to join a Mixer stream or something you might want to purchase from the store, all of that is determined for you by the Personalizer service. And since that was introduced to Xbox, the Xbox team has seen a significant lift in the engagement metrics of players on the Xbox service. Personalizer is also used to optimize the placement of ads in Bing search and the way that news appears in MSN News, again, with great improvements. But now you can use Personalizer in your own applications as well. Personalizer implements an AI technique called reinforcement learning, and let's see how that works. So suppose we want to display a hero action to the user, and the user probably isn't sure what to do next, so we could display one of several different suggestions, and in the gaming app that might be play a game or watch a movie or join a clan. And then based on that user's history and other contextual information like their location or the time of day and the day of the week, the service will rank the possible actions and then suggest the best one to promote. So in this case, that's join. And now hopefully that user will be happy, but how can we be sure? And that depends on what the user does next and whether that was something we wanted them to do. So we can get to define our own business logic, where we can assign something called a reward score between 0 and 1 to what happens next. For example, if we want people to spend more time playing games or reading articles or spending more time in the store, we would assign a higher reward score to that. And then Personalizer feeds that information back into the ranking system for the next time we need to feature an activity. But this isn't just a recommender system. Recommender systems have that unfortunate feature that they just kind of tell the user what they've already done. If you ever search for shoes on the web and then every product ad you get is for shoes, that's recommendation systems in action. This is different. So what Personalizer does is it's usually in something called explore mode, where it recommends the best activity based on the history and all we just saw. But sometimes it enters something called explore mode and presents the user with new things they may not have otherwise seen. And it's kind of like an automated A/B test system, but with more than 2 branches and all being tested in real time. So you control what the percentage is of the time that the explore mode is activated, and that controls how often the user will see new things they haven't otherwise seen. So what we did, as you can see in the source code for the Tailwind Traders app, is that for anonymous users, we're going to use the time of day, the day of week, and the browser operating system as context to influence those rankings. And for the reward score, we use whether or not they clicked on the hero panel, so just a 0 or 1. And so what will happen then is over time, Personalizer will determine what is the best category to present to anonymous users based on their time of day of week, and their operating system based on that activity. And then 20% of the time, try other things to see if we can get users to engage with other stuff. So to see that in action, I'm going to go back to the Tailwind Traders website here. And what I didn't mention before is that the list of products you see down there in that recommended section has been determined by the Personalizer service. In this case, electrical department is the one that's appearing there first. And we can see what's going to happen with the explore behavior if I click refresh. Now, it turns out it was already in explore mode, and now it's showing me the one that it actually recommends the most, which is Garden Center. Turns out the people that visit the website most were clicking on Garden Center a lot, so that's the one that appears more and most often. But I just keep on refreshing this a few times. Eventually, it'll go back into explore mode again, and we'll see that our app, based on Personalizer, is going to choose a different department to feature in the hero section. And I think from my recording that happens the next time. There we go. Plumbing appears as one. So we can see how users engage with that. Super easy to implement, super easy to use. Check out the code that I have on the website. Just to wrap up, if you're thinking about putting these AI services into production, there are lots of things you might want to be thinking about. Probably the first thing you want to think about is the cost. The short story here is that if you're just testing this out as a developer, most of the services I've shown you are free. But if you do want to go into production volumes, talking about millions of hits a second or very large documents to analyze, the pricing for that varies by service and region, and have a look at that bottom link on the screen to find out what the specific cost is for your application. You might also want to think about where your data is going and how it's used. For all of these inference services where we provide data and we get back a result, the data is uploaded to Azure and then just immediately discarded. You can get all the details about that in this compliance website that I have right here. But if you're working in a low bandwidth environment where sending up a big image across the web is an issue, or you work in a regulated environment where you can't send your data out of your firewall for whatever reason, There is another option that's available to you, which is to deploy with containers. For some of the Azure Cognitive Services, they are available as downloadable containers, which you can put behind your own firewall. So you send the data to them, it sends its results back. Nothing ever leaves your system except for billing data. And the cost is exactly the same as if you'd used Azure Cognitive Services online. And lastly, I've saved the most important consideration for last. You've seen how easy it is to integrate AI capabilities into your apps, but as they say, with great power comes great responsibility. It's really important to understand the impact your application has on people and consider the ethical implications. So if you're working with AI technologies like these or any others, you should be working within an ethical framework that focuses on enabling people to achieve more, is inclusive of all types of users, and is fair and transparent. Now, if you don't have an ethical framework set up already, a great place to start is Microsoft's own principles for AI, which you can read more about at that link right there. All right, to finish, I hope you've seen that with this pre-built AI, you can solve 80% of your needs for capabilities and apps really quickly. If you're interested in the remaining 20% and building your own apps, your own AI systems rather, have a look at the next 2 talks in this series. I hope you've learned that pre-built AI isn't magic, it's just data and numbers. But understanding how that data is used is really key to understanding its capabilities and limitations. And you don't need to be a rocket scientist to hook up to these APIs and get AI into your systems, but do think about how your app will be used and impact people. A few slides just with some links. If you'd like to check out all the documentation for cognitive services, it's available at that link right there. If you'd like to run through some courses on MS Learn about the AI systems, there's a great collection here, and that link is in the resources. And have a look at the rest of the talks in this session to learn about all the other things you can do with artificial intelligence as well. Thanks for your time. Thank you very much.